Millions of stars and planets surround us, each one keeping its own mysteries and incredible views. However, these space objects have a darker, more frightening aspect beyond their stunning appearance. In the deepest parts of space, we find planets so unusual and terrifying that they challenge everything we thought we knew about what makes a planet. Picture worlds where glass shards rain down sideways at incredible speeds, or places wrapped in never-ending darkness where starlight can't reach the surface. There are massive gas planets with air pressure strong enough to crush anything before it could land, and rocky worlds with constantly moving lava oceans beneath burning skies. These aren't the calm blue spheres with fluffy white clouds, or the red neighbor planets we've admired for years. These are places with conditions so extreme that nature creates environments deadly enough to seem like they came from our worst nightmares. If you enjoy the content, leave a like and subscribe to the channel. Come with us as we discover the most frightening and mysterious planets in space. Trace 2b, the darkest planet. Trace 2b stands as one of the darkest known planets outside our solar system, making it an interesting subject for anyone curious about space mysteries. This planet sits about 750 light-years from Earth in the Draco constellation. Scientists first spotted it in 2006 using the Transatlantic Exoplanet Survey, which looks for planets by watching how stars dim when planets pass in front of them, a technique called the transit method. This space body circles its star every 2.5 days, showing how incredibly close it orbits. Only about 3 million miles away, much nearer than Mercury is to our Sun. What makes Trace 2b different from other planets is how little light it reflects. Scientists have found that it bounces back less than 1% of the light hitting it, making it blacker than coal or any other planet or moon we know of in our solar system. This darkness comes mainly from its atmosphere, which holds light-eating chemicals like vaporized sodium and potassium, plus it has no clouds. This light absorption makes its surface extremely hot, reaching over 1,800 degrees Fahrenheit, placing it among the hottest planets we've discovered. Despite being so dark, Trace 2b has an unusual feature that keeps it from being completely invisible. The planet gives off a weak red glow because the extreme heat makes it emit light, similar to glowing coals in a fire. This glow adds to Trace 2b's mysterious appeal for both astronomers and casual sky watchers. Because Trace 2b orbits so close to its star, it experiences tidal locking. This means one side always faces the star in constant daylight, while the other side stays in endless night. This permanent split between day and night creates dramatic temperature differences across the planet, likely causing powerful winds and complicated weather patterns unlike anything we understand from Earth. Trace 2b's atmospheric conditions are equally fascinating. The vaporized metals like sodium and potassium, combined with no reflective clouds, suggest an atmosphere that's both alien and hostile by Earth's standards. Scientists think the planet might also have exotic cloud types made from completely foreign compounds, possibly adding to its dark look. Finding these elements and compounds in the atmosphere gives important clues about the chemical reactions happening on Trace 2b, helping us understand how the planet formed, changed over time, and exists today. Studying Trace 2b also helps us understand planets beyond our solar system in general. By comparing Trace 2b with other distant planets, scientists can explore how diverse planetary systems are in our galaxy. For example, Trace 2b's extreme features show the huge variety of possible planet types, from those with thick, heavy atmospheres to rocky, empty ones, or even water-covered worlds. These comparisons are essential for fully understanding how planets form and whether life could exist elsewhere in the universe. Trace 2b's unique characteristics make it a perfect target for future studies with better telescopes and equipment. The James Webb Space Telescope and other ground observatories are ready to give us better views of planets like Trace 2b. Future observations will probably give us more detailed information about the planet's atmosphere, surface conditions, and maybe even hints about its geological activity. 55 Cancri E, the Diamond Planet. As we continue exploring space, we travel to 55 Cancri E, a planet that captures our imagination with its remarkable features. Located roughly 40 light-years away in the Cancer constellation, 55 Cancri E is a world of extremes. A super-Earth about twice Earth's size and 8 times its mass. This intriguing planet orbits its host star, 55 Cancri A, so closely that 1 year there takes only 18 hours, very different from our 365-day trip around the Sun. What sets 55 Cancri E apart among distant planets isn't just its size or incredibly short year, but its possible surface conditions, which have earned it nicknames like Diamond Planet. Scientists theorize that the intense pressure inside 55 Cancri E could turn carbon into diamond, creating a world that literally sparkles with these precious stones. This idea comes from observations and models suggesting the planet is rich in carbon, along with other elements. While the romantic idea of a diamond planet captures our imagination, it's important to remember this is just a theory, one of many ideas that researchers want to test with better observation tools. The temperature on 55 Cancri E is another aspect that fascinates both scientists and regular people. With surface temperatures climbing over 4,000 degrees Fahrenheit, this planet is far from friendly to life as we know it. The extreme heat caused by being so close to its star means any atmosphere present is unlike anything in our solar system, possibly made of heavy gases in a supercritical fluid state, a state that blurs the line between gas and liquid. As we dig deeper into the mystery of 55 Cancri E, it's clear this planet holds many secrets that challenge what we know about planetary systems. Its close orbit around its star, just 1.5 million miles away, puts it in a category called ultra-short period planets. This closeness leads to one of 55 Cancri E's most interesting aspects. The tidal forces between the planet and its star are so strong that the planet is probably tidally locked. This means one side constantly faces the star in never-ending daylight, while the other side stays in eternal darkness. The sharp contrast between the day side and night side of 55 Cancri E has major effects on its climate and atmospheric behavior. Scientists think the temperature difference could create supersonic winds that carry heat from the scorching day side to the cooler night side. This extreme weather system could result in a complex and dynamic atmosphere unlike anything seen in our own solar system. Adding to 55 Cancri E's mystery is what its atmosphere is made of. Early observations suggested water vapor was present, but newer studies hint at an atmosphere rich in hydrogen, with layers possibly containing hydrogen cyanide, which indicates carbon-rich environments. These findings further support the idea that 55 Cancri E could indeed be a diamond planet, with a carbon-heavy interior that might transform into diamond under the planet's extreme pressure and temperature. The possibility that 55 Cancri E has an atmosphere rich in carbon compounds not only interests scientists but also makes us imagine what other types of worlds could exist in the vast reaches of our galaxy. Studying this planet is at the cutting edge of planet research, pushing the limits of current observation technology and theories about how planets form and what they're made of. Gliese 581c, a potentially habitable super-Earth. Going further into these mysterious planets, we encounter Gliese 581c. Found in 2007, Gliese 581c orbits the red dwarf star Gliese 581, located about 20 light-years away in the Libra constellation. This planet is particularly notable for sitting in its star's habitable zone. the area where conditions might be right for liquid water to exist, a crucial ingredient for life as we know it. Gliese 581c is about 1.5 times Earth's size, making it a super-Earth, and has a mass around 5.5 times our planet's. These measurements suggest Gliese 581c has much stronger gravity than Earth, which would greatly affect the planet's atmosphere and potentially any water or life forms there. The planet completes one orbit around its star in just under 13 days, showing it's close to Gliese 581 and raising interesting questions about its climate and atmospheric conditions. One of the most captivating aspects of Gliese 581c is the chance that it might have liquid water, an idea that depends on the planet's temperature and air pressure. If conditions are just right, Gliese 581c could have oceans, rivers, or lakes, environments that on Earth are full of life. However, scientists also warn that the planet's close orbit could mean it's tidally locked, with one side always facing its star and the other in constant darkness. This could create extreme temperature differences across the planet, with one side possibly too hot and the other too cold for liquid water to exist. As we look deeper into the mysteries surrounding Gliese 581c, we uncover layers of complexity that challenge and expand our understanding of livable worlds. The interesting possibility of this planet being in its star's habitable zone does more than just spark imagination. It drives forward the scientific quest to understand the conditions under which planets can support life. Studying Gliese 581c, along with other planets in the Gliese 581 system, offers rich opportunities for understanding the variety of planetary environments. The concept of a tidally locked planet, which Gliese 581c might be, introduces fascinating scenarios for climate and weather patterns. On such a world, the stark difference between the perpetual day and eternal night sides could create powerful atmospheric movements. Scientists think that if the planet has an atmosphere, it might move heat from the day side to the night side, potentially allowing for a more even temperature distribution than expected. This could create a twilight zone, a region where temperatures might allow for liquid water and possibly life. The challenges of exploring a planet like Gliese 581c are huge, given how far it is from Earth and the current limits of our technology. However, projects and missions in development aim to launch telescopes that can observe distant planets directly, analyzing their atmospheres for signs of water vapor, oxygen, methane, and other gases that might indicate biological processes. Such observations could provide indirect evidence of life or, at minimum, of environments where life as we know it could exist. Furthermore, studying Gliese 581c contributes to our understanding of red dwarf stars and their planetary systems. Red dwarfs are the most common star type in the Milky Way, and their long lifespans provide a stable environment for potentially livable planets. However, their tendency to produce powerful flares could threaten the atmospheres of closely orbiting planets, stripping away the very conditions necessary for life. Understanding how planets like Gliese 581c withstand their stellar environments is crucial for assessing the habitability of planets around red dwarfs. Proxima Centauri b, our closest exoplanet neighbor. Located in our cosmic neighborhood, Proxima Centauri b offers a tantalizing glimpse into the potential for life beyond Earth. Orbiting Proxima Centauri, the nearest known star to the Sun at just 4.24 light-years away, this planet captures the imagination and curiosity of scientists and space enthusiasts alike. Discovered in 2016, Proxima Centauri b sits in the habitable zone of its star, where temperatures could allow for liquid water to exist on its surface under the right atmospheric conditions. This intriguing world is approximately 1.3 times Earth's mass, suggesting it's a rocky planet much like our own. The close proximity to its star means Proxima Centauri b completes an orbit in just 11.2 Earth days, presenting a scenario where the planet could be tidally locked. This would mean one side of the planet always faces the star in perpetual daylight, while the other side remains in endless night. The effects on climate, weather, and potential habitability are significant, sparking discussions and studies aimed at understanding this unique environment. Despite the excitement surrounding Proxima Centauri b, the red dwarf star it orbits is known for its temperamental nature, often releasing powerful flares. These stellar outbursts could pose major challenges to the potential for life, possibly stripping away the atmosphere or exposing the surface to high radiation levels. Yet, the possibility remains that, under the right conditions, Proxima Centauri b could support an atmosphere that protects it from these harsh stellar winds, preserving the potential for habitability. Given its proximity to its host star, Proxima Centauri b is subjected to intense stellar radiation, much more than Earth receives from the Sun. This factor plays a crucial role in determining the planet's atmosphere and surface conditions. If Proxima Centauri b has a strong magnetic field, similar to Earth's, it could shield the planet from some of this harmful radiation, making it a more hospitable environment than initially thought. The existence of water, in any form, on its surface would be a groundbreaking discovery, significantly boosting the potential for life. The intriguing aspect of Proxima Centauri b's orbit, potentially being tidally locked, raises questions about the climate dynamics on such planets. The concept of a permanent day side and a permanent night side suggest extreme weather conditions, with possible effects on atmospheric circulation patterns that could distribute heat around the planet. Scientists hypothesize that if Proxima Centauri b has an atmosphere, it might have a temperate zone at the boundary between the light and dark sides, where conditions could be right for liquid water and, by extension, life. The ongoing and future missions aimed at exploring Proxima Centauri b are equipped with sophisticated instruments designed to detect the faintest signals of an atmosphere and analyze what it's made of. Spectroscopy, a method used to identify the chemical makeup of a planet's atmosphere by studying light from the star as it passes through, could reveal the presence of molecules like oxygen, carbon dioxide, and methane, all of which could hint at biological processes. The prospect of sending a probe to Proxima Centauri b, although decades away, sparks the imagination. Such a mission would provide direct observations and data, offering insights into the planet's geology, atmospheric conditions, and potential signs of life. Current initiatives like the Breakthrough Starshot project aim to develop the technology necessary to send small, light-powered spacecraft to the Alpha Centauri system, of which Proxima Centauri is a part, marking a monumental step in interstellar exploration. Pi Mensae c, a super-Earth in a multi-planet system. Venturing further into the cosmos introduces us to Pi Mensae c, a compelling planet that holds its own unique place within the vast collection of known celestial bodies. Discovered orbiting the star Pi Mensae, located some 60 light-years away in the Mensa constellation. This planet is part of a growing list of worlds that challenge and expand our understanding of planetary systems beyond our own. Pi Mensae c is particularly notable for being a super-Earth, a type of planet with a mass higher than Earth's, but considerably lower than the ice giants Uranus and Neptune. Its discovery, announced in 2018 through data from NASA's Transiting Exoplanet Survey satellite, TESS, marked a significant achievement in the search for planets beyond our solar system. Pi Mensae c has a mass around 4.82 times that of Earth and completes an orbit around its star every 6.27 days, showing it's very close to its host star, much closer than Mercury is to the Sun. What makes Pi Mensae c fascinating isn't just its size or orbit, but its position within a system that also hosts a gas giant, Pi Mensae b, discovered in 2001. This setup provides a rich field for studying the behavior of multi-planet systems, especially with such contrasting types of planets, a super-Earth and a gas giant, living around the same star. The differences in their compositions, orbits, and potential atmospheres offer a wealth of data for scientists trying to understand the variety of planetary environments that exist in our galaxy. Despite being close to its host star, the question of Pi Mensae C's habitability or its potential to have an atmosphere remains open. Its close orbit suggests it could be subjected to intense stellar radiation, possibly affecting any atmosphere it might have. However, the detailed study of its atmospheric composition, which could reveal the presence of gases like water vapor or carbon dioxide, has yet to be conducted. These studies are crucial for assessing not just the conditions on Pi Mensae C, but also the potential for life on planets that share its characteristics. Fomalhaut b, the zombie planet. The story of Fomalhaut b is as mysterious as it is fascinating. Initially discovered in 2008 through observations by the Hubble Space Telescope, it was celebrated as one of the first planets outside our solar system directly imaged, offering a glimpse into the methods of detecting and studying distant worlds. However, the planet's existence soon became a matter of debate. Unlike the rocky or gas giants found in our solar system, Fomalhaut b didn't give off any infrared radiation, a strange fact that puzzled scientists. Infrared radiation typically shows a planet's heat, which can be used to figure out its size and what it's made of. The mystery deepened when further observations failed to spot the planet consistently. It seemed to disappear and reappear in different data sets, behaving more like a ghostly apparition than a solid space object. This led to a sensational turn in 2012 when researchers proposed that Fomalhaut b might not be a planet at all. Instead, it could be a vast dust cloud resulting from a massive collision between two icy bodies orbiting Fomalhaut. This hypothesis painted a picture of a cosmic demolition derby, with Fomalhaut b as the fleeting evidence of a dramatic event. But the story doesn't end there. The debate continued to evolve with more observations and studies. Some astronomers hold on to the planet hypothesis, suggesting that Fomalhaut b might be a planet shrouded in a huge dust cloud, perhaps from a massive ring system or the aftermath of an impact, which could explain the unusual observations. This theory keeps the door open for Fomalhaut b's planetary status, suggesting it might be a world unlike any we've encountered. The journey of discovery surrounding this distant world showcases the leaps in astronomical techniques and the persistent curiosity that drives the scientific community forward. After its initial detection, the story of Fomalhaut b became a catalyst for debate and innovation, encouraging astronomers to refine their methods of observing and interpreting data from the far reaches of space. Advancements in telescope technology and imaging techniques have been at the forefront of this quest. The Hubble Space Telescope, with its unparalleled view of the universe, free from the distortions of Earth's atmosphere, played a pivotal role in the story of Fomalhaut b. Yet, the intrigue of Fomalhaut b pushed scientists to look beyond conventional methods. The application of dynamic imaging and the pursuit of infrared signatures using other space and ground-based telescopes added layers of complexity to the investigation, illustrating the multifaceted approach required to study such elusive targets. The scientific interest in Fomalhaut b also highlights a broader theme in astronomy: the search for planets beyond our solar system and the conditions that might support life. Each discovery, each unusual finding encountered in the vastness of space, brings us closer to understanding our place in the universe. The peculiar case of Fomalhaut b, with its disputed nature and the mysteries surrounding its existence, serves as a bridge to ponder deeper questions about planet formation, the diversity of planetary systems, and the potential for habitable worlds beyond our solar system. Moreover, Fomalhaut b's story is a testament to the dynamic nature of the universe. If indeed the result of a massive impact, it reminds us of the constant changes occurring on cosmic scales of time and space, shaping and reshaping the architecture of galaxies. The potential for new worlds to be born from the debris of such catastrophic events, or for existing planets to be cloaked in dust clouds, enriches our understanding of planetary evolution and survival in the harsh environment of space. Methuselah, HD 140283, the ancient star. Deep within the universe, there exists a star that seems almost out of place in the cosmic story due to its sheer age. This character is not a mythical figure but a star, known affectionately as Methuselah, or more formally as HD 140283. Methuselah's story captivates not just because of its age, but because it challenges our understanding of the cosmos, offering a paradox that has puzzled astronomers for years. Methuselah is intriguing because its age, estimated to be around 14.5 billion years, appears to defy logic. This estimation puts it at nearly the same age as the universe itself, which, according to current cosmological models based on the Big Bang Theory, is about 13.8 billion years old. The apparent puzzle of a star older than the universe prompts a deeper dive into the methods used to determine stellar ages and the uncertainties inherent in these measurements. The age of Methuselah was estimated using a technique that involves measuring its composition and its movement. Stars, much like people, change as they age, and by understanding a star's composition, particularly its metallicity, or the abundance of elements heavier than helium, astronomers can infer its age. Methuselah has an unusually low metallicity, indicating it formed when the universe was very young and contained few elements beyond hydrogen and helium. The star's speed and trajectory also offer clues to its ancient origin, suggesting it belongs to the halo of the Milky Way, a population of stars that surrounds the galaxy and includes some of its oldest members. The apparent age discrepancy of Methuselah has led scientists to refine their methods and question their assumptions. It has sparked discussions about the precision of age-dating techniques, the interpretation of data, and even the models of stellar evolution. This ongoing debate exemplifies the dynamic nature of science, where unusual findings challenge established theories and drive the quest for greater understanding. In addressing the Methuselah paradox, researchers have considered various factors that might affect their age estimates, such as the star's initial composition and the impact of its environment. Adjustments to the models of stellar evolution and more precise measurements of the star's properties have narrowed the age gap, suggesting Methuselah may be slightly younger than initially thought, but still remarkably ancient. WASP-12b, a doomed hot Jupiter. WASP-12b, a distant and exotic world far beyond our solar system, presents a stark contrast to the celestial bodies we've previously explored. This intriguing planet, discovered in 2008, orbits the star WASP-12, located approximately 600 light-years away in the Auriga constellation. What makes WASP-12b stand out in the vast catalog of planets beyond our solar system is its classification as a hot Jupiter, a type of gas giant that orbits very close to its host star, leading to extreme atmospheric conditions. With a mass almost 1.4 times that of Jupiter but an orbital period of just over a day, WASP-12b's proximity to its star results in surface temperatures soaring above 2,200 degrees Celsius. This intense heat has profound effects on the planet's atmosphere and structure, causing it to take on an elongated shape rather than a perfect sphere. Scientists have observed that the high temperatures on WASP-12b lead to the presence of heavy metals like iron and magnesium in its atmosphere, elements that in cooler gas giants would condense into clouds. Another remarkable feature of WASP-12b is its tidal interactions with its host star. The gravitational forces at play are so strong that the planet is being gradually pulled closer, leading to a scenario where WASP-12b may eventually be consumed by WASP-12. This grim fate isn't immediate, but the process provides a fascinating glimpse into the life cycle of planets beyond our solar system and their stars. WASP-12b also plays a crucial role in the study of planetary atmospheres. Its detection and analysis have been made possible through transit observations, where the planet passes in front of its host star from our perspective, allowing astronomers to study the starlight that filters through the planet's atmosphere. This method has revealed much about WASP-12b's composition and behavior, offering insights into the chemistry of other hot Jupiters. WASP-12b was discovered through the Wide-Angle Search for Planets (WASP) project, a ground-based effort designed to detect planets outside our solar system using the transit method. The transit method involves monitoring the brightness of stars over time and looking for periodic dimming, which indicates that a planet is passing in front of the star from the observer's perspective. This method is particularly effective for identifying planets that orbit close to their host stars, as these planets tend to transit more frequently and produce more noticeable changes in brightness. In the case of WASP-12b, astronomers observed the slight dip in the brightness of its host star, WASP-12, which occurs every 1.1 days, the period it takes for the planet to complete an orbit around its star. The regularity and depth of these dips in brightness provided clear evidence of a planet's presence and allowed scientists to calculate its size and orbital distance. Follow-up spectroscopic observations, which analyzed the star's light to detect the gravitational pull of the planet, confirmed the planet's mass and further details about its characteristics. The discovery of WASP-12b was significant because it added to the growing list of planets beyond our solar system that challenge our understanding of planet formation and behavior, particularly those in close orbits around their stars. It also underscored the effectiveness of the transit method and ground-based telescopes in contributing to the science of planets beyond our solar system, a field that has rapidly expanded since the first such planets were confirmed in the 1990s. KLT-9b, the hottest known exoplanet. Discovered by the Kilodegree Extremely Little Telescope, KELT survey, KLT-9b orbits a star some 670 light-years away in the Cygnus constellation. This planet is not only remarkable for its sheer size, closely resembling that of Jupiter, but it's also distinguished by its extreme temperatures and the peculiar nature of its orbit around a blue A-type star, one of the hottest stars known to host a planet. KLT-9b's discovery unveiled a world where daytime temperatures soar above 4,300 degrees Celsius, about 7,800 degrees Fahrenheit, hotter than many stars and setting the record for the hottest planet beyond our solar system discovered to date. Such blistering temperatures are attributed to the planet's close proximity to its host star, KLT-9, which it orbits every 1.5 days. This rapid orbit places KLT-9b in a category of ultra-short period planets, experiencing conditions that are beyond the extremes found in our own solar system. The intense radiation from its host star has profound effects on the planet's atmosphere. Studies suggest that the ultraviolet light is so powerful it can split molecules apart, preventing the formation of many chemicals common in cooler planetary atmospheres and leading to a predominantly atomic composition. This has piqued the interest of astronomers, as it provides a unique laboratory for studying atmospheric chemistry under extreme conditions. Moreover, KELT-9b's atmosphere contains ions such as ionized iron and titanium, unusual for planetary atmospheres and indicative of the extreme heat that can ionize metals. The presence of these metals in gaseous form provides insights into the planet's atmospheric behavior and the types of chemical reactions that can occur under such intense radiation. As we further explore the mysterious nature of KLT-9b, the planet's relationship with its host star takes center stage, revealing a dynamic and potentially catastrophic future. The extreme temperatures and rapid orbit of KLT-9b are just the beginning of its story. The gravitational forces exerted by its host star, KELT9, are causing tidal interactions that have profound implications for the planet's structural integrity and long-term survival. These tidal forces are not only responsible for KELT9b's elongated shape, but also contribute to the gradual decay of its orbit. Over time, it is expected that KELT9b will spiral closer to its star, leading to increased heating and atmospheric loss. This process, known as orbital decay, could ultimately result in the planet being consumed by its star. Such a fate underscores the temporary nature of some planetary systems beyond our solar system, offering a glimpse into their life cycle and evolution. The study of KELT9b also sheds light on the mechanisms of atmospheric escape. The intense heat and radiation from KELT9 are powerful enough to strip away the planet's atmosphere, atom by atom, into space. This atmospheric escape is observable as a tail of gas being blown off the planet, similar to a comet's tail, providing direct evidence of the harsh conditions that prevail. Furthermore, the peculiarities of KELT9b extend to its night side, which remains a subject of intrigue. Despite the extreme temperatures on its day side, the night side of the planet experiences significantly cooler, though still extremely high temperatures. This discrepancy poses questions about the efficiency of heat distribution across the planet's atmosphere and the potential for complex atmospheric dynamics involving winds and jet streams. The exploration of KELT9b has broad implications for our understanding of planetary atmospheres, particularly those orbiting close to their stars. It challenges astronomers to develop models that can accurately predict the behavior of planets under such extreme conditions, contributing to our broader understanding of planetary science. Kepler-10b, the first rocky exoplanet. Continuing our journey in space, we encounter Kepler-10b. Identified by the Kepler Space Telescope, which was tasked with discovering Earth-like planets in habitable zones, Kepler-10b orbits its star some 560 light-years away in the Draco constellation. This planet holds the distinction of being one of the first rocky planets confirmed outside our solar system, providing a glimpse into the diverse planetary compositions that exist beyond our familiar celestial neighborhood. Kepler-10b is a world of extremes, with a mass 3.3 times that of Earth, yet it orbits its star at a distance more than 20 times closer than Mercury is to our Sun. This close proximity results in a year on Kepler-10b lasting just 0.84 Earth days and contributes to surface temperatures that can exceed 1,300 degrees Celsius, about 2,372 degrees Fahrenheit, far too hot to support life as we know it. The planet's surface is thought to be molten in some areas, with possibly oceans of lava, a testament to the intense heat generated by its star. The discovery of Kepler-10b was significant for several reasons. It was the first planet found by the Kepler mission to have both its size and mass measured, allowing scientists to calculate its density and confirm its rocky nature. This achievement marked a milestone in planet research beyond our solar system, offering evidence that rocky planets not only exist outside our solar system but can also be detected and studied with the technology at our disposal. Building upon the discovery of Kepler-10b, the exploration of this intriguing planet opens doors to deeper questions about the nature of planets beyond our solar system. The methods used to uncover Kepler-10b's secrets, particularly the transit method, where the planet's passage in front of its star leads to a slight dimming of the star's light observed by telescopes, underscore the sophistication of current astronomical techniques. This process not only revealed Kepler-10b's presence but also provided insights into its composition and physical characteristics, highlighting the potential for further discoveries. Kepler-10b's extreme proximity to its host star raises fascinating questions about its formation and history. How did it end up in such a close orbit? Theories suggest that it might have migrated inward from a more distant orbit over millions of years, a journey that could have dramatically altered its composition and surface features. This scenario prompts a reevaluation of our understanding of planetary system dynamics and the forces that shape them over time. Furthermore, the study of Kepler-10b has implications for the search for life beyond Earth. While this planet itself is inhospitable to life as we know it, due to its scorching temperatures, its detection demonstrates the capability to find and analyze Earth-sized and potentially habitable planets in other solar systems. This effort is part of a broader quest to identify worlds where conditions might be right for life, a pursuit that continues to motivate astronomers and captivate the public imagination. Venus, Earth's hellish twin. Now, let's take a step back and explore some of the more familiar planets. Venus, our celestial neighbor, presents a fascinating contrast to Earth, offering a unique perspective on planetary science and the conditions necessary for life. Known as the second planet from the Sun, Venus orbits within our solar system's inner circle, positioned closer to the Sun than Earth. This proximity to our star contributes to Venus's status as the hottest planet in our solar system, with surface temperatures averaging around 465 degrees Celsius, 869 degrees Fahrenheit. Such extreme conditions are primarily due to its dense atmosphere, composed mostly of carbon dioxide, with clouds of sulfuric acid, creating a runaway greenhouse effect that traps heat. Despite being similar in size and composition to Earth, earning it the nickname Earth's twin, Venus's surface and atmospheric conditions are vastly different. Its rotation is notably slow, taking about 243 Earth days to complete a single rotation on its axis, which is longer than its orbital period around the Sun of about 225 Earth days. Intriguingly, Venus rotates in the opposite direction to most planets in our solar system, including Earth, meaning the Sun rises in the west and sets in the east on Venus. The exploration of Venus has been a challenging endeavor due to its harsh environment, with numerous missions attempting to study the planet up close. Soviet Venera probes in the 1970s and 1980s provided the first detailed images of its surface, revealing a world covered with volcanic landscapes, vast plains, and high mountain ranges. Recent studies suggest Venus is still geologically active, with potential signs of recent volcanic activity. Venus also exhibits a phenomenon known as ashen light, an apparent faint glow of its dark side when viewed from Earth, which has been a subject of speculation and study among astronomers for centuries. Additionally, the planet's thick clouds reflect sunlight efficiently, making Venus the third brightest object in the sky visible from Earth, after the Sun and the Moon. Neptune, the distant ice giant. Neptune stands as a sentinel in the outer reaches of our solar system, the eighth planet from the Sun and the most distant among the known planets following the reclassification of Pluto as a dwarf planet. Discovered in 1846, its existence was predicted mathematically before it was visually confirmed, a testament to the power of Newtonian mechanics and a milestone in the history of astronomy. Neptune is 4 times wider than Earth, with a diameter of about 49,244 kilometers, 30,598 miles, making it the smallest of the gas giants in our solar system, yet it packs a dense atmosphere composed primarily of hydrogen and helium, with traces of methane giving it a striking blue hue. Orbiting the Sun at an average distance of 4.5 billion kilometers, about 2.8 billion miles. Neptune takes approximately 165 Earth years to complete a single orbit, which means it has only completed one orbit since its discovery. Despite its distance from the Sun, Neptune's atmosphere is surprisingly active, with dynamic weather systems and the fastest winds in the solar system. reaching speeds of up to 2,100 kilometers per hour, about 1,300 miles per hour. This activity is thought to be driven by the planet's internal heat, rather than solar energy, which is minimal at such a great distance. Neptune's magnetic field is also a subject of interest, as it is tilted significantly relative to its rotation axis and offset from the planet's center, similar to the magnetic field of Uranus. This unusual magnetic orientation may be the result of the planet's internal structure and heat distribution, offering clues about the processes occurring within its deep interior. The planet is encircled by a faint system of rings and 14 known moons, with Triton being the largest and most notable. Triton orbits Neptune in a retrograde direction, meaning it moves in the opposite direction of the planet's rotation, suggesting that it may have been captured by Neptune's gravity and is not a native moon. Triton is geologically active, with cryovolcanoes that eject nitrogen gas and dust particles from beneath its surface, creating a thin atmosphere that, like Neptune's, is mostly nitrogen. The exploration of Neptune has been limited, with the Voyager 2 spacecraft providing the bulk of our current knowledge during its flyby in 1989. The data collected by Voyager 2 revealed Neptune as a world of immense beauty and complexity, with swirling clouds, high-altitude ice crystals, and dark spots indicative of storm systems. These observations have laid the groundwork for future missions that may further unravel the mysteries of this distant planet, deepening our understanding of the outer solar system and the forces that shape it. Uranus, the sideways planet. Uranus, the seventh planet from the Sun, offers a fascinating study in contrasts and surprises within our solar system. Discovered in 1781 by William Herschel, its discovery expanded the known boundaries of our solar system for the first time in modern history. Unlike the more familiar rocky planets of the inner solar system or the gas giants like Jupiter and Saturn, Uranus is often categorized as an ice giant. This classification comes from its unique composition, primarily of water, ammonia, and methane ices, beneath a thick atmosphere of hydrogen and helium. One of the most striking features of Uranus is its dramatic tilt. The planet rotates on its side with an axial tilt of about 98 degrees, meaning it essentially rolls around the Sun on its orbit. This peculiar orientation leads to extreme seasonal variations, with each pole getting around 42 years of continuous sunlight, followed by 42 years of darkness. This tilt is believed to be the result of a massive collision with an Earth-sized object long ago, which drastically altered the planet's orientation. Uranus is encircled by a complex system of rings, less prominent than Saturn's but equally intriguing. These thin, dark rings were only discovered in 1977, highlighting how much remains to be learned about this distant planet. Additionally, Uranus is accompanied by 27 known moons, each named after characters from the works of William Shakespeare and Alexander Pope, adding a cultural layer to the scientific exploration. Despite its distance and the challenges it presents for observation, Uranus has been visited once by a spacecraft Voyager 2 in 1986. This flyby provided a wealth of data, revealing many of the planet's secrets and leaving many questions unanswered. The pale cyan color of Uranus, due to the methane in its atmosphere which absorbs red light and reflects blue, and its calm appearance belie a complex atmospheric system with the fastest winds in the solar system, reaching speeds of up to 900 kilometers per hour, around 560 miles per hour. Pluto, the beloved dwarf planet. Pluto, once the ninth planet from the Sun in our solar system, has captivated the curiosity and imagination of astronomers and the public alike since its discovery in 1930 by Clyde Tombaugh. Located in the Kuiper Belt, a region filled with icy bodies and remnants from the solar system's formation, Pluto is a dwarf planet, a category that it helped define when the International Astronomical Union (IAU) refined the criteria for planethood in 2006. Despite its reclassification, Pluto continues to be a subject of significant scientific interest and exploration, embodying the mysteries that lie at the edge of our solar system. With a diameter of about 2,377 kilometers, 1,477 miles, Pluto is smaller than Earth's moon. Its orbit is highly elliptical, taking it on a 248 Earth-year journey around the Sun, during which it can come closer to the Sun than Neptune for a period before moving back to its more distant position. This unique orbit contributes to Pluto's complex and variable environment. Pluto's surface is surprisingly diverse, with vast plains, towering mountains, and deep valleys. One of the most striking features is a heart-shaped glacier named Sputnik Planitia, composed of nitrogen ice, which hints at a geologically active world beneath its icy exterior. The presence of mountains made of water ice, which behaves like rock due to the extremely low temperatures, suggests geological processes that have yet to be fully understood. The dwarf planet's atmosphere is thin and composed mostly of nitrogen, with traces of methane and carbon monoxide. As Pluto moves away from the Sun, its atmosphere freezes and falls to the surface as snow, a seasonal change that provides insight into the dynamics of planetary atmospheres under extreme conditions. Pluto's 5 known moons, Charon, Styx, Nix, Kerberos, and Hydra, add another layer of intrigue to its story. Charon, the largest of these moons, is so sizable in relation to Pluto that they are often considered a double dwarf planet system. The gravitational dance between Pluto and Charon presents a fascinating dynamic, with both bodies orbiting a point in space between them, rather than Pluto being the sole center of orbit. The exploration of Pluto, particularly by the New Horizons spacecraft in 2015, has opened a new chapter in our understanding of the outer solar system. New Horizons flyby provided unprecedented detail about Pluto's surface, atmosphere, and moons, shedding light on a world that is far more complex and dynamic than previously imagined. Io, Jupiter's volcanic moon. Jupiter's moon Io stands as a celestial body of extreme contrasts and profound fascination within our solar system. Discovered in 1610 by Galileo Galilei alongside 3 other moons orbiting Jupiter, Io marks itself as the innermost of the Galilean moons and is heralded for its dramatic geological activity. This moon, slightly larger than Earth's own moon, is characterized by over 400 active volcanoes on its surface, making it the most volcanically active body in our solar system. The source of this intense volcanic activity lies in the powerful gravitational tug-of-war between Jupiter and the other Galilean moons, Europa and Ganymede, which causes immense tidal heating within Io's interior, flexing and heating its interior to keep its mantle and core in a molten state. Io's surface is a tapestry of sulfur and sulfur dioxide frost, giving it a colorful appearance with yellow, red, white, black, and green hues, unlike any other celestial body we know. This vivid landscape is constantly being reshaped by volcanic eruptions that can eject plumes of material up to 500 kilometers, about 310 miles, into space, creating extensive basins and depositing large amounts of sulfur in various forms. Despite its hostile environment, Io plays a crucial role in our understanding of geological processes beyond Earth. It challenges scientists to reconsider notions of planetary and moon formation, the conditions necessary for volcanic activity, and the potential for life in extreme environments. The study of Io has also provided insights into the magnetic and gravitational interactions within the Jupiter system, particularly how Io contributes to Jupiter's magnetic environment by generating an electric current known as the Io flux tube, which produces intense auroras on Jupiter. The exploration of Io has been primarily through flyby missions, most notably by the Voyager spacecraft in the late 1970s and the Galileo orbiter in the 1990s and early 2000s. These missions have offered glimpses into Io's complex and dynamic environment, revealing a world where the ground is literally never still. Continuing our exploration of Io, Jupiter's fascinating moon, we delve deeper into the implications of its unique geologic and volcanic features. The immense volcanic activity on Io is not just a spectacle of nature's power, but also a window into the internal dynamics of celestial bodies. The heat generated by tidal forces within Io's interior leads to frequent and massive volcanic eruptions, shaping a landscape that is constantly being renewed and reformed. This process offers scientists a live laboratory to study how volcanic activity can affect a body's surface, atmosphere, and even its potential habitability. One of the most striking discoveries about Io is the presence of lava lakes and vast flows of molten rock that cover large portions of its surface. These features indicate that Io's mantle must be incredibly hot, with some estimates suggesting temperatures exceeding 1,200 degrees Celsius, about 2,192 degrees Fahrenheit, in certain areas. The composition of these lavas, rich in silicates and sulfur compounds, differs from the typical basaltic flows found on Earth, providing clues about the moon's formation and the elemental makeup of the outer solar system. Io's influence extends beyond its own orbit, impacting Jupiter's magnetosphere. The moon ejects about 1 ton of material into space every second through its volcanic plumes, contributing to a torus of plasma that encircles Jupiter. This interaction not only fuels Jupiter's auroras, but also creates a complex electromagnetic environment that challenges our understanding of planetary magnetospheres. The study of Io has broader implications for the search for life beyond Earth. While Io itself is too hostile for life as we know it, its volcanic activity underscores the diverse conditions under which moons and planets can exist. Understanding Io helps refine our models of celestial dynamics and habitability, informing the search for life-supporting environments in other star systems. Future missions to the Jupiter system, such as the European Space Agency's Jupiter Icy Moons Explorer and NASA's Europa Clipper, aim to further explore Io and its fellow Galilean moons. These missions will provide new insights into Io's volcanic activity, its interaction with Jupiter's magnetic field, and the moon's role in the larger Jovian system. Io remains a symbol of the dynamic and active processes that can exist on moons throughout the universe, challenging our perceptions of where and how dynamic geological activity can occur. Its study enriches our understanding of the solar system, offering lessons on the forces that shape celestial bodies and the potential for discovering even more worlds of wonder beyond our own. Titan, Saturn's Earth-like moon. Saturn's moon Titan stands as one of the most intriguing and distinctive bodies in our solar system, capturing the fascination of scientists and space enthusiasts alike. As the largest moon of Saturn and the second largest in the solar system, Titan is unique in having a dense atmosphere, thicker than that of Earth, composed mainly of nitrogen with traces of methane and hydrogen. This thick atmosphere obscures the moon's surface from view in visible light, requiring radar and infrared instruments to peer through the haze. What sets Titan apart from all other moons in our solar system is its complex weather system, including rain, rivers, lakes, and seas, though not of water, but of liquid methane and ethane. This discovery has led to Titan being one of the most Earth-like worlds we know of, albeit with a frigid surface temperature averaging around -179 degrees Celsius, -290 degrees Fahrenheit. Despite these chilly conditions, Titan's atmosphere and surface processes mirror those of Earth's own water cycle, with evaporation, cloud formation, and precipitation shaping the landscape. Titan's surface is varied and includes vast dunes of hydrocarbon sands, mountain ranges, and a multitude of liquid hydrocarbon lakes in the polar regions, making it an object of intense scientific study. The presence of liquid bodies on Titan makes it a prime candidate in the search for life beyond Earth, particularly in exploring the chemistry that could lead to life. The Cassini-Huygens mission, a collaboration between NASA, ESA, European Space Agency, and ASI, Italian Space Agency, has been instrumental in unveiling Titan's secrets. When the Huygens probe descended onto Titan's surface in 2005, it provided humanity's first close-up view of this alien landscape, revealing a complex world with features reminiscent of Earth, such as river channels and stones smoothed by liquid erosion. This exploration of Titan has opened up new questions about the Moon's past and present, including the sources of its methane, the mechanisms driving its climate and geological processes, and the potential for hosting simple forms of life in its vast liquid reservoirs. Delving deeper into the mysteries of Titan, Saturn's largest moon, we find a world that continues to captivate with its potential for scientific discovery. Beyond its Earth-like weather systems and hydrocarbon lakes, Titan holds clues to the solar system's history and the complex chemistry that could lead to life. One of the most intriguing aspects of Titan is its subsurface ocean, believed to lie beneath the icy crust. This hidden ocean, possibly composed of water mixed with salts and ammonia, represents a key interest for scientists searching for life beyond Earth. The interaction between the liquid water ocean and the rocky mantle beneath could create conditions suitable for chemical reactions foundational to life as we know it. The study of Titan is not just about understanding another world in our solar system. It's also about gaining insights into Earth's past and the potential for life elsewhere in the universe. Titan's thick atmosphere, rich in organic molecules, acts as a window into the chemical processes that might occur on planets beyond our solar system with similar conditions. The complex organic chemistry occurring in Titan's atmosphere and on its surface, driven by sunlight and possibly by cryovolcanism, creates a vast array of compounds that could be precursors to more complex molecules associated with life. Future missions to Titan, such as NASA's Dragonfly mission slated for launch in the 2030s, aim to explore its chemistry and habitability further. Dragonfly is a drone-like rotorcraft designed to fly through Titan's dense atmosphere, covering much greater distances than a traditional lander or rover could. Its goals include studying chemistry that could lead to life and habitability at various locations, analyzing the Moon's surface and subsurface properties, and investigating its atmospheric and surface processes. By directly sampling Titan's environment and conducting detailed analyses, Dragonfly seeks to unlock the secrets of this enigmatic moon, potentially reshaping our understanding of life's origins and existence beyond Earth. Oumuamua, the interstellar visitor. Oumuamua is a fascinating object that captured the world's attention when it was discovered on October 19, 2017, by astronomers using the Pan-STARRS 1 telescope in Hawaii. Its name, Oumuamua, comes from the Hawaiian term for scout or messenger from afar arriving first, reflecting its status as the first known interstellar object to pass through our solar system. What sets Oumuamua apart from other celestial bodies observed by scientists is its highly elongated shape. Unlike any comet or asteroid seen in our solar system, and its surprising acceleration as it traveled away from the Sun, behavior not typically expected from a natural celestial object without any visible signs of outgassing or a tail. Measuring roughly 800 meters long and only about 80 meters wide, Oumuamua's cigar-like shape is unprecedented. Observations and analyses suggest it is a dark red color, indicative of a surface rich in organic molecules that may have been irradiated by cosmic rays for millions, if not billions, of years. Its exact origin remains a mystery, but it's believed to have been ejected from another stellar system before making its solitary journey through the cosmos and eventually passing by Earth. The trajectory and speed of Oumuamua, combined with its non-gravitational acceleration as it moved away from the Sun, sparked intense debate and speculation among astronomers. Some theories suggest that its acceleration could be attributed to outgassing, a process common in comets where ice turns into gas and drives the comet forward. However, the lack of a visible comet-like tail or coma around Oumuamua challenged this explanation, leading to a variety of alternative theories, including the less conventional suggestion that Oumuamua might be an artificial object. The intrigue surrounding Oumuamua deepened as further analysis of its properties and behavior continued to challenge conventional understanding of comets and asteroids. One of the most perplexing aspects of Oumuamua was its rotation. Observations indicated that it was tumbling, rather than smoothly rotating, and its brightness varied dramatically, suggesting that it was highly elongated and possibly flat, rather than cigar-shaped as initially thought. This unusual rotation and shape hinted at a violent past, perhaps involving a collision that sent it hurtling out of its original stellar system and into interstellar space. Another point of intense debate among scientists is the origin of Oumuamua. While it's clear that it came from outside our solar system, pinpointing its exact home has proven to be challenging. Some theories propose that Oumuamua could be a fragment from a larger object that was torn apart during a close encounter with a star or planet, while others suggest it might be a remnant of a planetary building block that never formed into a full-fledged planet. The diversity of theories reflects the limited data available and the novelty of studying such an object, underscoring the need for continued observation and research on interstellar visitors. Oumuamua's brief visit also highlighted the limitations and capabilities of current astronomical technologies and the importance of being prepared for future encounters with interstellar objects. Since its departure, there has been a concerted effort within the scientific community to enhance observation techniques and develop strategies for rapidly responding to similar phenomena. This includes proposals for missions that could intercept or rendezvous with incoming interstellar objects, providing unprecedented opportunities for up-close study and potentially answering long-standing questions about the composition and nature of material from other star systems. In reflecting on the Oumuamua encounter, it's clear that this mysterious visitor has had a lasting impact on astronomy and our understanding of the cosmos. It has sparked conversations about the need for international cooperation in monitoring the skies for future interstellar objects and the potential for groundbreaking discoveries that such objects hold. As technology advances and our ability to detect and study these visitors from afar improves, we stand on the brink of a new frontier in our quest to understand the universe and our place within it. Eris, the dwarf planet that redefined our solar system. Eris, nestled far beyond the familiar planets of our solar system, invites intrigue and mystery as one of the most distant known dwarf planets. Discovered in 2005, Eris significantly contributed to the redefinition of what constitutes a planet, leading to the demotion of Pluto to the status of a dwarf planet. Located in the scattered disk, a remote area of the solar system, Eris orbits the Sun at a distance so vast that it completes a single orbit approximately every 558 years. This celestial body is named after the Greek goddess of discord and strife, a fitting title considering the astronomical debate its discovery sparked. Eris measures about 2,326 kilometers in diameter, making it slightly smaller than Pluto but remarkably dense, suggesting it is primarily composed of rock and ice. This composition hints at the conditions and materials present in the outer solar system during its formation. One of the most fascinating aspects of Eris is its surface, which is exceptionally reflective, suggesting it is covered in a thin layer of frozen methane. Observations indicate that Eris's surface undergoes changes in brightness as it moves away from the sun, which could be due to the sublimation of surface ice into gas, altering its reflectivity. Eris has one known moon, Dysnomia, named after the daughter of the Greek goddess Eris, representing lawlessness. The discovery of Dysnomia played a crucial role in determining Eris's mass, which is found to be approximately 27% greater than that of Pluto. This measurement was instrumental in understanding more about the dwarf planet's characteristics, including its density and composition. The story of Eris is not just about a distant dwarf planet. It is a narrative that reshaped our understanding of the solar system. Its discovery prompted the International Astronomical Union to redefine the criteria for planethood in 2006, which now requires a celestial body to orbit the Sun, be spherical in shape, and have cleared its orbit of other debris. Eris's presence in the Kuiper Belt, a region teeming with icy bodies, challenged the notion of what it means to dominate an orbit, contributing to the creation of the dwarf planet category. Diving deeper into the exploration of Eris, we delve into the scientific endeavors and future prospects surrounding this distant world. The intrigue surrounding Eris extends beyond its pivotal role in the reclassification of Pluto. It represents a frontier of discovery in the outer reaches of our solar system, where the conditions are starkly different from those of the inner planets. One of the most compelling aspects of Eris is its atmosphere. Observations suggest that Eris possesses a tenuous atmosphere of nitrogen and methane, similar to that of Pluto. This atmosphere is thought to expand when Eris approaches closer to the Sun along its elliptical orbit and freeze onto the surface as it moves away. This dynamic process offers valuable insights into atmospheric physics in extremely cold environments, far from the warmth of the Sun. Eris's orbit, taking it as far as 97 astronomical units, AU, from the Sun, 1 AU is the average distance from the Earth to the Sun, places it in a region of space that is difficult to study. Despite the challenges, the New Horizons mission to Pluto and the Kuiper Belt has sparked interest in missions that could explore Eris and other distant objects. Such a mission would not only shed light on Eris itself, but also on the nature of the scattered disk, a less understood region of the solar system that is home to many other icy bodies. The study of Eris and its comparison with other dwarf planets like Pluto and Haumea is crucial for understanding the diversity of objects in our solar system. Each of these bodies has unique characteristics, from their geological features to their atmospheres and moons, offering clues about the processes that dominate in these distant reaches. For instance, the similarities and differences between the atmospheres of Eris and Pluto can help scientists understand how atmospheric conditions evolve in response to their orbits and distances from the Sun. Looking to the future, Eris holds the potential to answer key questions about the solar system's formation and evolution. Its composition, particularly the ratio of rock to ice, can provide insights into the materials present in the outer solar system during its early history. Additionally, studying Eris's surface features, such as craters and possible cryovolcanoes, could reveal the impact history and internal processes of this remote dwarf planet. Advancements in telescope technology and the possibility of dedicated missions to the Kuiper Belt and beyond mean that our understanding of Eris is poised to grow. The James Webb Space Telescope, with its unprecedented sensitivity and resolution, is expected to offer new views of Eris, potentially uncovering features that have remained elusive. Sedna, the mysterious distant object. Sedna, an enigmatic object within our solar system, offers a fascinating glimpse into the vast and largely unexplored region beyond Neptune. Discovered in 2003, Sedna's orbit is one of the most distant and eccentric, taking it from about 76 astronomical units, AU, at its closest approach to the Sun, to an astonishing 936 Australian dollars at its farthest, a journey that takes approximately 11,400 Earth years to complete. This extraordinary orbit challenges our understanding of the solar system's formation and the forces shaping its outer boundaries. With a diameter estimated to be about 1,000 kilometers, Sedna is smaller than Pluto, classifying it as a dwarf planet, though it has yet to be officially designated as such by the International Astronomical Union. Its surface is one of the reddest in the solar system, suggesting the presence of organic molecules or tholins, which are complex compounds that form when ultraviolet sunlight irradiates simple organic compounds such as methane and ethane. The discovery of Sedna was significant because it resides in a region of space that was previously believed to be largely empty. Its presence, along with that of other distant objects discovered since, suggests the existence of a vast and previously unknown population of similar bodies in the outer solar system, sometimes referred to as the inner Oort cloud or sednoids. These objects could be remnants from the early solar system, providing critical clues about its formation and the distribution of small bodies beyond Neptune. One of the most intriguing aspects of Sedna's discovery is the insight it offers into the gravitational influences at the edge of our solar system. The peculiar orbit of Sedna, which does not bring it close enough to be significantly affected by Neptune or the other giant planets, suggests that either it was perturbed by a yet undiscovered massive object far beyond Neptune, or it was captured from another star during the Sun's early history in a dense star cluster. One of the most tantalizing theories that Sedna's discovery has fueled is the possibility of a yet undiscovered ninth planet, sometimes referred to as Planet 9. This hypothetical planet is theorized to be influencing the orbits of Sedna and other distant objects through its gravitational pull. If it exists, Planet 9 could be several times the mass of Earth, lurking unseen in the dark regions far beyond Neptune. The search for this elusive planet involves complex simulations and observations, aiming to explain the anomalies in the orbits of Sedna and similar objects. Sedna's long journey around the Sun also offers a unique opportunity to study the Sun's influence over vast distances. As Sedna moves closer to the Sun in its eccentric orbit, it could potentially develop a very faint coma or atmosphere, much like comets do when they approach the Sun. Observing these phenomena could provide insights into the composition of Sedna and the mechanisms by which bodies in the solar system interact with solar radiation and the solar wind, even at extreme distances. Moreover, Sedna's existence challenges and refines our models of the solar system's early dynamics. It supports the hypothesis that the Sun was once part of a dense star cluster, where close encounters with other stars could have dramatically affected the orbits of the outer solar system's objects. Alternatively, Sedna's peculiar orbit could be the result of interactions with unseen celestial bodies, or even a passing star, suggesting a more chaotic early solar system than previously thought. The exploration of Sedna and the quest to understand its origins and properties highlight the dynamic and ever-evolving nature of our solar system. Each discovery brings with it new puzzles and propels our scientific capabilities and curiosities further into the cosmos. Future missions, possibly involving flybys or even orbiters, could one day unravel the mysteries of Sedna, offering unprecedented insights into our solar system's outer reaches and its formation. Kepler 1625b, the planet with a giant moon. Kepler 1625b is a planet beyond our solar system that has captured the attention of astronomers and the public alike due to its intriguing characteristics and the possibility that it hosts a moon similar to a giant version of our own Earth-Moon system. Discovered by the Kepler Space Telescope, which was launched by NASA to search for Earth-like planets orbiting other stars, Kepler 1625b resides in the Cygnus constellation, approximately 4,000 light-years from Earth. The planet orbits its host star, Kepler 1625, a star similar to our Sun but larger and older, every 287 days, a period that places it in or near the habitable zone of its star, where liquid water could potentially exist. Kepler 1625b is a gas giant, several times the size of Jupiter, making it a type of planet known as a hot Jupiter, although its specific conditions and temperature depend heavily on its atmosphere and distance from its star. The most striking aspect of Kepler 1625b's discovery was the potential detection of a moon orbiting the planet, which would be the first moon outside our solar system ever identified, colloquially known as an exomoon. This possible exomoon, unofficially named Kepler 1625bi, is estimated to be the size of Neptune, making it an unprecedented find, as moons of this size are not found in our solar system, and it challenges existing theories of moon formation. The detection of the exomoon is based on transit observations, where the planet and its moon pass in front of their host star, causing a temporary dimming of the star's light that can be measured from Earth. The data suggests that the moon's gravitational pull influences Kepler 1625b's orbit around its star, leading to variations in the timing and duration of the transits. These observations have sparked considerable interest and debate in the scientific community, with further analysis and additional observations needed to confirm the existence of the moon and understand its characteristics. The intrigue surrounding Kepler 1625b and its potential exomoon extends into the realm of what these celestial bodies can teach us about the cosmos. The study of such an unusual moon, especially one that rivals Neptune in size, could revolutionize our understanding of moon formation theories and the dynamics of planetary systems far beyond our own. The very notion that moons could be as large as planets introduces a fascinating complexity into the architecture of solar systems, suggesting a diversity in celestial formations that was previously unimagined. Further investigations into Kepler 1625b and its potential exomoon are crucial for astronomers seeking to unravel the mysteries of planetary systems beyond our solar system. Observations and models suggest that the formation of such a large moon might involve processes distinct from those that gave rise to the moons in our solar system. For instance, it could have formed from a disk of gas and dust surrounding Kepler 1625b in its early stages, or it might even be a captured rogue planet ensnared by Kepler 1625b's gravitational pull. The presence of this exomoon could also have significant implications for the environment of Kepler 1625b itself. If confirmed, it would provide a rare opportunity to study the interactions between a planet and its moon in a system very different from our own. For example, the gravitational forces between the planet and the moon could affect their rotational dynamics, leading to tidal heating, which might influence the internal geology and atmospheric conditions of the moon. Moreover, the potential habitability of such an exomoon sparks curiosity and speculation. While Kepler 1625b, a gas giant, is unlikely to be habitable, its moon, if it has a rocky composition and an atmosphere, could present conditions conducive to life, at least theoretically. The prospect of an exomoon with an environment that could support life adds an exciting dimension to the search for life beyond Earth, expanding the focus from planets to their moons. The quest to confirm the existence of the exomoon and understand its nature involves sophisticated observational techniques and future space missions. Telescopes such as the Hubble Space Telescope and the James Webb Space Telescope play pivotal roles in this endeavor, offering the high-resolution imaging and spectroscopy needed to detect and characterize distant planets and their moons. These observations, combined with advanced computer modeling, will help scientists piece together the story of Kepler 1625b and its companion, shedding light on the formation and evolution of complex planetary systems. KELT 11b, the inflatable planet. KELT-11b is a fascinating planet beyond our solar system discovered by astronomers using the Kilo-degree Extremely Little Telescope survey, which specializes in finding planets around bright stars. Located approximately 320 light-years away from Earth in the Sextans constellation, KELT-11b orbits the star KELT-11, a bright, evolved star that is nearing the end of its life cycle. This proximity to its host star provides a unique opportunity for scientists to study the planet's atmospheric composition in detail. KELT-11b is classified as a hot Jupiter, a type of gas giant planet that is similar in characteristics to Jupiter but orbits very close to its star, resulting in much higher surface temperatures. However, KELT-11b stands out among hot Jupiters due to its extremely low density. It is one of the least dense planets beyond our solar system ever discovered, with a density so low that it is nearly as inflatable as a balloon. This low density suggests that the planet has a very extended atmosphere, making it an excellent target for atmospheric studies. The planet's close orbit around its host star, completing a full revolution in just under 5 days, subjects it to intense stellar radiation. This proximity not only contributes to its high temperature but also likely affects its atmospheric behavior, potentially leading to atmospheric escape, where the outer layers of the atmosphere are blown away by stellar wind and radiation. KELT-11b's large radius, nearly 40% larger than Jupiter's despite its lower mass, and its extended atmosphere provide a rare opportunity to analyze the chemical makeup of a planet's atmosphere beyond our solar system. The atmosphere's extended nature allows for the detection of various molecules through the process of transmission spectroscopy, where scientists observe the starlight that passes through the planet's atmosphere during transits. This method can reveal the presence of water vapor, carbon monoxide, and other important compounds, offering insights into the planet's formation and evolution. The intrigue surrounding KELT-11b extends into the implications of its findings for the broader field of planet research beyond our solar system. The exceptional characteristics of KELT-11b, particularly its low density and extended atmosphere, serve as a model for understanding the physics and chemistry of hot Jupiters. These insights are pivotal in piecing together the evolutionary puzzle of gas giants under intense stellar radiation, offering clues about their atmospheric retention, heat distribution, and potential for atmospheric escape over time. One of the most compelling aspects of studying KELT-11b is what it can teach us about the life cycle of planetary atmospheres. The extended atmosphere of KELT-11b, exposed to extreme conditions, may undergo processes that are not observed in the atmospheres of more dense and compact planets. For instance, the phenomenon of atmospheric escape, where lighter molecules are stripped away from the planet by the star's radiation, is likely occurring at a significant rate on KELT-11b. Understanding this process gives scientists valuable insights into how planets lose their atmospheres and the timescales over which this transformation can happen, which has implications for the habitability of planets over their lifetimes. The study of KELT-11b's atmosphere through transmission spectroscopy opens a window into the chemical and thermal structures of hot Jupiter atmospheres. The detection of specific molecules, their distribution, and how they interact with incoming stellar radiation can inform models of atmospheric behavior and chemistry. These models, in turn, help scientists predict the conditions on similar planets yet to be observed in detail, broadening our understanding of planetary atmospheres across the galaxy. The research into KELT-11b and its atmospheric properties also underscores the importance of future telescope missions and the development of new observational technologies. Instruments such as the James Webb Space Telescope, JWST, and the upcoming Extremely Large Telescopes, ELTs, on the ground are poised to provide even more detailed observations of KELT-11b and other planets beyond our solar system. These advanced tools will enable the detection of fainter signals and the identification of more complex molecules in planetary atmospheres, further enriching our understanding of their composition and behavior. The HR 8799 system, a young solar system. The HR 8799 system is an extraordinary and pioneering discovery in the field of astronomy, offering a fascinating glimpse into a planetary system that mirrors a young version of our own solar system. Located about 129 light-years away in the Pegasus constellation, this system is centered around HR 8799, a young main-sequence star that is slightly more massive and brighter than our Sun. The HR 8799 system is particularly renowned for being one of the first where multiple planets beyond our solar system were directly imaged, marking a significant milestone in the study of planetary systems beyond our own. Discovered incrementally between 2008 and 2010, the HR 8799 system consists of 4 massive planets, known as HR 8799 E, D, C, and B, moving in orbits far from their parent star. These planets are gas giants, with masses ranging from about 7 to 10 times that of Jupiter, making them some of the largest planets beyond our solar system discovered to date. Their orbits range from relatively close to the star to more extended orbits, with the outermost planet, HR 8799b, orbiting at a distance comparable to Pluto's orbit in our solar system. One of the most striking features of the HR 8799 system is the direct imaging of its planets. Unlike the majority of planets beyond our solar system detected through indirect methods like the transit or radial velocity techniques, the planets of HR 8799 were observed directly using powerful telescopes equipped with adaptive optic systems. These systems correct the blurring effect of Earth's atmosphere, allowing for clearer images of celestial objects. The direct imaging of these planets has provided astronomers with invaluable data regarding their atmospheres, compositions, and orbital dynamics. The planets of the HR 8799 system are young, with estimated ages of around 30 million years. This youthfulness means they are still glowing with residual heat from their formation, making them easier to observe with infrared telescopes. Observations have revealed that these planets have complex atmospheres with clouds and possibly even weather systems, similar to what is found in the gas giants of our solar system. Moreover, the HR 8799 system is surrounded by a vast debris disk composed of dust and ice, which is thought to be the remnants of the process that formed the planets and possibly hints at the presence of additional, smaller bodies within the system. Continuing the exploration of the HR 8799 system, we delve deeper into the scientific significance and the future prospects of studying such a uniquely detailed planetary system. The HR 8799 system's direct imaging provides an unprecedented opportunity to study the atmospheric composition, orbital mechanics, and even the climate of planets beyond our solar system in great detail, offering a wealth of information about how planetary systems develop and evolve over time. The atmospheres of the HR 8799 planets are of particular interest to astronomers. Spectroscopic analysis, which examines the spectrum of light emitted or absorbed by the planets, can reveal the presence of various gases and potentially provide clues about atmospheric dynamics and weather patterns. For instance, the detection of water vapor, methane, and carbon monoxide in these planets' atmospheres would not only confirm theories about the chemical makeup of gas giants, but also offer insights into the processes that dominate their weather and climate systems. The HR 8799 system's debris disk plays a crucial role in understanding the formation and evolution of planetary systems. By studying the distribution and composition of the debris disk, scientists can infer the presence of other, smaller bodies within the system, such as asteroids or comets, which may impact the development of the system's planets. The disk also provides clues about the late stages of planetary formation, offering a glimpse into the processes that may have occurred in the early solar system. The future study of the HR 8799 system will benefit significantly from advancements in telescope technology and observation techniques. Projects like the James Webb Space Telescope, JWST, and ground-based telescopes equipped with next-generation adaptive optics will be able to capture even more detailed images and spectra of the HR 8799 planets. These observations will enhance our understanding of the planet's atmospheres, including their compositions, temperature profiles, and potential weather phenomena. The study of the HR 8799 system has implications for the search for life beyond Earth. While the gas giants themselves are unlikely to host life as we know it, their detailed study can inform our understanding of the habitability of other planetary systems. By learning how gas giants and their moons form and evolve, scientists can better assess the potential for habitable environments elsewhere in the galaxy. Conclusion: the endless journey of discovery. As we near the end of this exploration, we are reminded that the universe is filled with mysteries waiting to be unraveled and wonders yet to be discovered. The quest to understand the cosmos and our place within it has never been more alive. With each passing day, new technologies and methodologies are being developed, opening up new possibilities for discovery and exploration. What lies beyond the next horizon? Only time and our relentless pursuit of the unknown will tell. But one thing is certain: the journey is far from over, and the best discoveries are yet to come. From the darkest planet Trace 2b to the potentially habitable Proxima Centauri b, from the diamond planet 55 Cancri e to the mysterious interstellar visitor Oumuamua. Each of these worlds challenges our understanding and expands our knowledge of what's possible in the universe. The volcanic fury of Io, the methane lakes of Titan, the scorching heat of KLT9b, and the icy mysteries of Sedna and Eris all remind us that the cosmos is far more diverse and surprising than we ever imagined. These planets, moons, and mysterious objects are not just distant curiosities. They are keys to understanding how planetary systems form, how atmospheres evolve, and where life might exist beyond Earth. They push the boundaries of our technology, inspire our imagination, and fuel our curiosity to explore further into the vast unknown. As we continue to develop more powerful telescopes, send more sophisticated missions into space, and refine our methods of detecting and studying distant worlds, we stand on the threshold of a new era of discovery. The universe awaits, with countless more secrets to reveal, and humanity's journey to understand it all has only just begun.